Chase Pipes, and you're watching Chasing History, brought to you by American Digger Magazine and the Smoky Mountain Relic Room. And we are at the University of Arizona Alfie, Norville Gem and Mineral Museum. This is a brand new museum that you guys have helped to get started. Would you guys mind introducing yourselves to the camera?
Absolutely. My name is Eric Fritz. I'm the director of the museum. I've also been involved in the design and build out of this space over the past 4 years.
And my name is Elizabeth Gass, and I'm the exhibit specialist here at the museum. So as we walk around, every piece that is out on display, I've had a hand in placing.
This is, seriously, you guys are in for a great treat, because this is an awesome museum. Not only the specimens that are here, but the way that they present it and educate the public is mind-blowing. So I know you guys want to go check it out. I want to go learn some more. Let's go check it out. So what kind of display do we have here? This is kind of the start of the museum. How does the museum start out?
Sure. So we've got 3 main galleries. The first one is mineral evolution, where we take the scientific theory that when the solar system formed, there were only 50 or 60 minerals. And that's remained constant in all of our study of space, meteorites, samples from the moon, and the spectroscopy that we're doing on Mars currently, all encompass that original 50 to 60.
So and this is throughout all of the universe, there's only 50 elements or minerals that are out in the expanse of the universe, basically?
Almost, because when we get to Earth itself, we have 5,600 and counting.
Really?
It's the only environment we found that supports the wide diversity that we find here on Earth.
That is just absolutely mind-blowing that across the entire expanse of the universe, you've just got these 50 minerals and elements. That is amazing. But yet here on Earth, we have so many to choose from. Let's get into this display case right here. What is this?
Sure, so our first case, we try to explore what we believe are those original 50 to 60 minerals. And I'll point out that they're not all obscure dark gray and black rocks. We know quartz, one of our most abundant minerals on Earth, would have been among the early. Also corundum, which encompasses ruby and sapphire. Spinel, which is another gem material that also is a beautiful mineral specimen. And what we found is the oldest mineral on Earth, zircon. Zircon we found in Australia that dates back over 4 billion years. So we know it was an early mineral.
And that's a dating method that people are using, is looking for the zircon crystals in order to date the age of the Earth.
Exactly, because zircon does have a small amount of radioactivity, so we're able to date things that have that radiocarbon radio element to them.
Okay.
The most interesting in this case, though, Chase, is opal. We've got a great example here. And opal, we know, has to form in conjunction with water. So when our solar system formed, there had to be some source of water.
So because you know you've got opal as one of those original 50 elements, you know that there must have been water present out there.
Water present. And we know from our understanding of early Earth, a lot of the ocean mass covered the Earth. How we've kind of come to find that opal had to be one of those originals is spectroscopy on Mars. We find microcrystalline spheres of opal all over the planet.
Really?
How cool is that?
Cool. So then that's also another indicator that there was water on Mars as well.
At one point, absolutely.
That's fascinating.
Absolutely.
This is a great way to start out to show that, there are, this is the main 50. But you were talking about there are 5,600 different minerals that are on this planet. How is that possible if we've only got the 50 here?
Right. So of course, everyone knows about geologic processes that over time minerals can form and change. Sedimentary, metamorphic, and igneous that we all learned about in elementary school and maybe didn't fully understand, like me. But it's also a coevolution with life. And as we move through, we'll see how oxygen played its part and the organisms that were present in early Earth really changed the mineralogy of Earth as well.
Okay, cool. Is there anything else in this display case you'd like to show us?
I think that pretty well covers it. We introduced meteorites, of course, and we'll let Elizabeth explain a little more about those next.
Okay. So we've got the meteorites here. What are so unique about the meteorites that you have and what they can tell us about life on this planet, or well, minerals on this planet and throughout the universe?
Yeah, so what's really cool about it is that meteorites are kind of like a time capsule to geologists. So when you have things here like this big chondrite, which chondrites are composed of something called a chondrule, and chondrules are literally little spheres of like the early dust of the solar system. And that's how we've been able to kind of tell, like, back when all the star stuff was coming together, what elements were actually there, which is really cool. So we take that, and when they fall to Earth, we can actually see what these little time capsules are telling us about how these early protoplanets were forming, or what they were made of, and things like our iron meteorites that, you know, like we have King and Diablo here in Arizona, which is a really famous meteorite and meteorite crater, that, you know, that would have been like the core of a planet that failed to be. So we were pretty lucky to not be in that little zone that that particular planet formed, because we're in the safety zone of the solar system, whereas that guy didn't make it.
Yeah. So because these meteorites fall to Earth, and we know the minerals that are within those meteorites, we only see the 50 that we were talking about before, correct?
Correct.
Okay, and that's how we can know that that's pretty much all that there is out there in the universe.
Right. So, and what's really cool about that is that, you know, seeing all these meteorites and things like that, they're very consistent. And that's what's really kind of crazy. And so, like, as we've learned more about Mars, we've actually been able to go back and go, oh, these really weird meteorites, we didn't know where they were from, are actually Martian. We just didn't know that before.
Wow.
So people have actually gone back and reclassified meteorites based on what we have now learned about different outer planets.
So when you look at a meteorite, you're like, oh wow, well this is Martian. How do you know it's Martian?
So the way that you can look at it is because of the textures that we see in different meteorites. We can tell if, like with a chondrite, a lot of them, you're just going to see like these little, you know, little balls in a microscope, and you know that basically that hasn't been heated enough to erase that texture. But once you start getting into like where it's been really heated, you start seeing textures and minerals that are actually in our crust here on Earth. And so with Martian meteorites and lunar meteorites, you can look at them and go, hey, we have some of these same rock types here on Earth. It's from a planet. Well, then you start looking at the chemistry of it, and because we know the chemistry of those two planets, we can go, oh, this is a piece of that particular planet or moon.
So because we know the chemistry of rocks on the moon and rocks on Mars, we can cross that with these meteorites that are found and say, oh, it's part of that.
Yeah.
Oh, that's so cool.
Which is really cool.
Yeah, that's easy. Okay, cool. All right, so what else on meteorites would you like to explain to us?
Well, so there's these beautiful textures in iron meteorites called Wiedemann's stocking pattern, and it is a mouthful. It's German.
Definitely a mouthful.
Yeah. But it is a iron nickel metals. There's two of them, and they're called camosite and taenite.
Okay.
And when you find these particular alloys of iron nickel metal, they only exist in space. They don't exist here on Earth. But it's a certain ratio and a certain type of iron and nickel alloy that we only find coming from outer space.
Is it because they formed in 0G?
So they didn't have, basically, they don't have like rust to them. They will rust once they're here on Earth and exposed to oxygen. But it's basically like a reduced iron. So like it's not the type of iron we find on Earth. And then basically because the environment that they formed in, they connected with nickel, and for some reason here on Earth, we just do not have one.
That's fascinating. That is really cool.
It's really cool.
So, okay, so we can look at the meteorites and we can tell that, you know, all right, we've got 50 minerals spread across in these meteorites. We know that's what's basically out in the solar system. That's what's out there. Now we've got 5,800, whatever the number was, 5,600 on the planet. How do we get only 50 out here and 5,600 here?
So basically you start off with early Proterozoic life. So you start with these 50 or 60 or so minerals, and when you start adding plate tectonics, volcanism, so we had all those volcanoes erupting, meteorite strikes, when you start talking about all these super, I hate to say violent, but a lot of times they're extremely violent, occurrences, you start getting these mixes of elements and pieces of these mineral puzzles that never were put together before, and suddenly they can connect and create something new.
Oh, that's cool. So do you guys have some displays that talk about that?
Yeah, we totally do.
All right, let's go check that out. So one of the big questions that I know I have and that everybody has is you've got these, because this is a mind-blowing statement to people, is that you see all these cool minerals all over the place, but out in the universe there's only 50, and we've got 5,600 here on Earth. That's a mind-blowing statement. So what are the processes? Why do we have so many here and very few out there?
Sure, so I think it revolves around a lot of the dynamic processes on Earth. We touched on geologic processes, but it's also Earth's very dynamic, and it's a coevolution with life. We have here a stromatolite fossil. Stromatolites are basically cyanobacteria that lived in the ocean. We know the Earth was covered primarily by ocean early on. These still exist today in Australia in an area called Shark Bay. But we know they date back 3.7 billion years. And they were responsible for the creation of these wonderful banded iron formations.
Okay,
as you can see on the back wall.
And so that's what this is banded iron?
This is called banded iron.
Okay.
This too is from Australia, and it represents the cyanobacteria basically exhaled oxygen. And they lived in an oxygen-free environment, so our planet would have been a lot like the other planets in the solar system that don't have oxygen. But by exhaling oxygen, basically we would build up an oxygen atmosphere around the Earth, then it might collapse, then it might reform, until it became stable like we know today, which is the only way to support advanced life forms, both plant and animal. It also changed the ionic state of the iron, which is the primary component here. And by changing that ionic state, it changed the elements that could combine with iron. We know, for example, water is hydrogen, 2 atoms to 1 oxygen. But in other forms, hydrogen peroxide is H2O2. It's able to combine differently depending on those different ionic states. And when that happened, we got several things happening as well. We ended up with a whole new suite of minerals because the iron would combine with elements it could never combine with before. It also provided the early stages of life itself as it progressed through those oxygenation effects. And that happened 2.5 billion years ago. So the cyanobacteria basically lived 1 billion years before it was able to oxygenate our planet.
Wow, that's crazy. But what it sounds like you're saying is that it's the introduction of new chemistry, I guess you could say.
Correct, yes.
That is allowing different things to happen.
Absolutely.
That's so fascinating. So if it wasn't for the oxygen present, or the oxygen that formed the iron, that started this whole process, we wouldn't have the diversity of minerals that we have today.
True, and we wouldn't be here either without oxygen. But yes, absolutely. It changed and made a whole new suite of minerals. And each time you change that suite of minerals, then they all combine and become more complex minerals as well.
So chemistry is hugely important in the formation of minerals.
To everything that we know on Earth.
Okay.
It's all about the chemistry.
This is why chemistry is important. Okay, all right, cool. So what do we got over in this showcases that?
So again, knowing that most of the surface was covered by oceans, that's where all of our elements basically concentrated over time. One great example is manganese. And we've got examples of manganese nodules here. So the manganese would have formed in the ocean sediments, and then as the oceans receded and the continents formed independently, those concentrated areas of magnesium would then combine with other elements, and we end up with a whole new suite of different minerals. Some of the most beautiful, the pinks, like rhodochrosite and rhodonite, the color is responsible from those magnesium as part of that chemical structure.
So basically, as the chemistry changes, the color changes, how it grows changes, because crystals, they are growing, is that correct?
So they grow based on the atomic bonds between the different elements. And what makes it fascinating is every mineral on Earth, whether it's in our body or out in the environment, falls into one of 7 different crystal systems, period. And then the chemistry varies, but they all follow that same rule of crystal symmetry, and then depending on which elements come together will determine the shape and the color many times.
That is fascinating. That's cool. Okay, all right. This is just too overwhelming. I mean, you've really got a great setup here. So what's the next step in your educational process for this museum? So, you know, you do a really fantastic job of explaining this. What's the next step for your educational tools?
So I think something else interesting, we've already seen that life and minerals have an interrelationship.
Okay.
So let's look at a specific example. We take the mineral flora apatite, which is the approved name. A lot of times we see it just called apatite, but a beautiful selection of different crystal forms and different colors. But what makes it most interesting is the mineral apatite is also responsible for our teeth and bones in our bodies and everything that has a skeleton and has teeth.
That's fascinating. So if it wasn't for this mineral here, we wouldn't have the teeth that we have.
We wouldn't be the same as we are. You know, it's hard to say if we'd all be soft-bodied invertebrates like a jellyfish, or if nature itself would have found another mineral that would have taken the place. But we know now that apatite, fluorapatite, is the building block of our structure.
And so that's because we, as living things on this planet, are consuming these minerals.
They're part of our process. Our DNA is able to capture the things we need that make us people, make plants plants, make lizards lizards, and make minerals minerals. So it's all a combination under the right conditions.
That's so fascinating. So when the next time somebody tells you to go eat rocks, say yes please. Because if it wasn't for the rocks, we wouldn't be what we are today. And if it wasn't for it's wildly, beautifully complicated.
It is.
You know how this all goes on. I don't know another way to explain it.
It's a very ordered universe and a very ordered system. We just can't really understand all those aspects.
Right. And so how these minerals are getting into our system is we're not literally, you know, a million years ago picking this up and chewing on it. You know,
Yeah.
it's found in the water, it's found in the other things that are living that we consume. Is that how does this get into our system?
Yeah, I mean, it's part of the great design of what makes us people and what makes rocks and minerals what they are. It's having the right, it's basically like cooking. You've got the right elements and you might end up with a lemon pound cake or you might end up with a red velvet. It just depends on what you put into it. Same with both our inorganic mineral world and our organic life as we know it.
Okay. So when someone says, you know, oh, my iron content in my blood is low, that's literal iron. Well, not literal iron, but...
Yeah, so we are given supplements that contain that element iron that then our body is able to process and reduce those levels. Same with calcium. You know, we might have an upset stomach. We take a calcium pill to settle our stomach. It comes from naturally formed calcite in our mineral world.
That's so cool! It's just a whole brand new way to look at
It is.
rocks and minerals and crystals. This is awesome.
You know, that's the one thing that I think we've done well. We built a story. Of course, starting with the solar system, our mineral heritage, but then how man sort of interfaces with minerals in the mineral world and makes our environment all the more interesting and good.
Well, let's go look at some of those.
Okay, excellent.
All right, come on. Okay, so tell us about the mineral diversity that we have here that you guys have on display.
Sure, so mineral diversity is another way of thinking. So we all know that the Amazon rainforest has all of this abundant plant and animal life, thousands of different species, versus an old growth forest in British Columbia. There's only 12 plants found there, the ferns, the trees, the conifers. We've done the same thing with minerals. So we've got a great example of peridot from right here in Arizona. The mineral is forsterite. That particular environment, there are only 6 minerals known. It's a volcanic environment. Versus Bisbee, Arizona, which has 330 different mineral species. It's the 3rd most abundant mineral locality in the entire world. It's separated by just over 100 miles. Why is there such a difference in concentration of minerals? Of course, we can explain it scientifically, but the reality is it's just the way it happens on Earth. And it's very fascinating in that regard. And then we take mineral diversity, we look at the supergroup of calcite or calcium-bearing minerals, and you can see in these 2 cases just a wide range of color, crystal shape, and crystal form. And then one of the big takeaways for our museum is looking at what mineral groups. So garnet, for example, is not really a mineral. It's a group of minerals that are all similar in crystal structure and in chemistry, but they're just different enough to give us all of these different colors, shapes, and forms. So we like to make sure that people understand that garnet is a group with about 11 different minerals in it, and sometimes we just lump them all together and say it's a garnet.
Oh, okay. Yeah, because there seems to be a lot of people just throwing all of this stuff into one category of mineral, when really chemically there's a lot more going on.
Absolutely.
Okay, that's fascinating. Now, you guys have got some really great electronic displays here at the museum. Could you show us
Yes, we do.
some of those?
Absolutely.
All right, let's go check those out. You know, one thing that's really impressed me about this museum is that you guys really have got state-of-the-art, up-to-date, you know, interactive displays. And this is a new one on me. I mean, are we bringing up our own bags or something? Or what's going on with this?
So basically, just like in a supermarket, we're taking an everyday object that everybody probably knows how to use now, since, you know, self-checkout is a big thing now. And you scan a barcode and it'll tell you exactly what mineral and the element that is a part of that product that we use every day.
So these are different everyday items that you guys have here, from a battery to a light bulb, a salt and pepper shaker, a lipstick.
Yeah, and then we've got
watches.
Yeah, like pencil, toothpaste actually, a watch, and then a ceramic mug.
Okay, and so you scan it like you did there, and it brings up, what does the graphic bring up, and what does this tell us?
So here it's showing that this is the part of the object that we're looking at. I'll scan it again. And so here we're looking at the tip of the pencil, which is made out of graphite. So when people say pencil lead, it's not actually in fact lead, it is graphite.
Okay.
Which is really closely related to diamond, except the structure is different.
Huh.
So with graphite, you have these really thin stacked layers that mean that when you scrape it across a piece of paper, you're actually scraping layers of graphite off onto the paper.
Really?
Yeah.
That's cool. Huh. So what else can people do if this just kind of lays it all? Oh, I touched it. I didn't mean to touch it. So this interactive lays out what all is in this display.
Right.
And then you can do that with any other, like with a salt and pepper shaker here, and it goes into all the different minerals that are found within a salt and pepper shaker.
Right. So here is
Awesome.
halite or salt. The halite is the mineral name for salt. And basically gives you the chemical formula, so NaCl. And then it tells you like how it forms, and then it shows you what it looks like in its natural state, and then how you might see it inside of your little salt and pepper container.
Wow, this is a great display. Let's look at some of the other ones. So this is another neat display. We've got some chemistry going on. We've been talking about this whole episode is just the chemistry, the chemistry, the chemistry. Why is the chemistry so important, and what does this display have to tell us about that?
Sure, so pretty much everything on Earth has some kind of crystal structure. There are a few exceptions to that. We got a great animation that was produced by a German high school student who was delighted to share that with all of our visitors, where he's showing time-lapse crystal growth. Earlier we talked about the fact that everything is one of 7 crystal systems. So you can see here, this is actually the hexagonal crystal system that we just passed over. And as Elizabeth just described with graphite, you can see these stacked layers of pure carbon atoms. That's all it's made out of, and they do kind of slough off. Versus diamond, which is exactly the same chemical composition, but a totally different crystal structure. So it's very important to how things form. And then we talked a little bit about color. So we've created this great interactive. By the way, all of our interactives we created in-house and then went to design and build teams. So they're very unique to us. But for crystal chemistry, we can take quartz, for example. And it shows a great example of quartz, tells how it forms, and then we can create our own. So we know that quartz forms from silicon and oxygen, and if we don't do anything else, we end up with beautiful, clear, transparent quartz. If we add just a tiny trace amount of iron into that crystal structure, we get amethyst.
Oh, that is neat.
And then if we have amethyst and it's exposed to heat naturally, then we end up with citrine, the beautiful yellow form of quartz. And then interestingly, if it's subjected to radiation, we think of it as natural radiation, but it can also be done by man. We end up with smoky quartz. And what happens with smoky quartz is the radiation actually distorts that perfect crystal structure and makes it askew. And then visually for us, it's brown.
Wow. So this display can take you through all those different steps to learn chemically why rock is one thing and
one color or another. And it's really interesting because as we've had collectors come through that have collected all their life, they never really understood what that cause of color was. And in less than a minute, they have a great understanding. We've made it simple enough that it's attainable for everyone.
And see, this is what I was saying, guys, at the beginning of this episode. This is educationally driven, but in a way that's just mind-blowing with what you will learn. I thought I knew rocks and minerals really well. My whole perspective and understanding has been blown by coming to this place. You guys have done a fantastic job.
Thanks, Chase, and I think you really hit on it. We want to educate, but like you, we want to inspire you to go out and learn more about some new concept that you've just been introducing.
Yeah. Now, one last thing I'd love to show people out there is you guys have some incredible, top-notch specimens in your collection. Before we sign off from our episode, can we see some of these awesome specimens that you guys have?
Absolutely. We'd love to share those.
All right, let's go check those out. So you guys are also known for your incredible mineral specimens that you have, and I've got to say my jaw is dropped. Show us some of these incredible specimens that you have. I didn't even know nature could do some of what it's doing right in front of me. What is going on here?
So most of these come from a particular type of geological formation called a pegmatite. And what a pegmatite is basically it's a volcanic feature where you kind of have like these pipes almost. And that transports a lot of this like super heavily like element laden fluid that often has like rarer elements in it. And so they're able to combine, and because some of the pockets are really large, you get really big, beautiful crystals inside. And so, because of some of those rare elements, you get really cool stuff like here, this big spodumene, and some of the other ones, like this number 13 in here, are lithium ores. And lithium is a little harder to find in the Earth's crust. And so a lot of times, if they're big and ugly and not nearly as pretty as this, they're ground up and made into lithium ore for batteries and things like that.
Really?
Yeah.
Wow, that's great. So they're finding specimens that aren't as nice as this,
Right.
and grinding them up for that.
Yeah, so what's really crazy is somewhere up in the Northeast, I forget exactly where, they were finding spodumene crystals that were like white-brown color, so nothing amazing.
Yeah.
But they were like 20 feet. And so they were, they were finding these massive crystals and grinding them up.
Wow.
And for the most part with these guys, don't cry too much over a 20-foot crystal being ground up. They were usually broken apart.
Okay.
So they're just finding like the big cast of them and taking whatever's in there and melting it.
I gotcha. What is going on here?
Yeah, so basically what you have here is you have an amethyst that is formed over top of something else. I could not tell you what, but whatever it is, maybe some sort of other quartz stalactite or something. But basically the stalactite split and then the amethyst formed over top of it and then left us with basically with bunny ears.
That's cool.
Which is really cool.
What about this guy right here? Okay.
So the this beautiful rubellite, which is basically, it's a type of tourmaline. And so rubellites are generally referred to as like your reds or very deep pink tourmalines. But so here you have like a fan of them, so they would have had enough room in a pocket to form all those different crystals all along inside of there, and then when those fluids disappeared, you're left with this basically like jackstraw pattern of crystals.
Whoa. And what about what's growing on top of it?
So that is lepidolite, and lepidolite is a lithium mica. So it's usually purple.
That's cool.
Yeah.
Yeah.
It's really cool.
What about this guy? Number 16.
Oh,
that?
That is a hydroxyl herderite.
What is that? I've never
So
heard of such magic.
I'm going to admit that I have not really, before I saw this one, I never really had heard of it.
Yeah.
So it's a really like oddball rare mineral. Again, this is probably the only one I've ever seen, but I know for a fact that it's extremely large for that species. But yeah, so these all come out of Brazil. But yeah, again, sorry, that one's kind of a weird one.
You stumped you.
You did.
Ah, sorry. All right, we gotta have you redeem yourself. All right, this bad mamma jamma right here. What is going on there?
Okay,
that is
so
awesome.
that is another beautiful tourmaline, and so that particular formation is really well known for having these like exquisitely zoned crystals. So what you're actually looking at is where you're seeing the pink is actually the interior core of the crystal, and then the outer core is that really beautiful like blue-green. And so it actually has a skin over top of the pink, but the pink is so bright and that skin is so thin in that section that you're seeing the color pop through.
Wow, that is too cool.
And then what else is going on here? Notice how some of them have kind of a pointy end and then others are flat?
Yeah.
So those flat ends are not cut, those are completely natural. Tourmalines can actually have a positive and a negative end, and that is referring to magnetism. So you can actually take a magnet and charge a tourmaline, basically, and take a magnet, and it'll repel from one end and attract from another end.
That's insane.
So yeah, so you can get positive and negative in tourmalines.
That's cool.
And that's also why, so I've got a blow dryer, like for drying my hair, and it has tourmaline in it because they actually will take ions out of the air and help make your hair not frizzy.
Really?
Yeah.
That's nuts.
Yeah.
That is cool. You guys have got the most amazing collection I've seen. And the way you guys explain this stuff and the way you have the museum set out is absolutely mind-blowing. I mean, this is an incredible collection and seriously worth coming and checking out. Let's say, just real quick, if people wanted to come visit, what are your hours of operations? When are you guys? How can people come see this? Do you have anything available online?
Yeah, so it's all online.
Okay.
So unfortunately, because we're newly open, we're still, like, we have our hours for now, but I would definitely, depending on when you guys see this video, check our hours because we'll be expanding them the longer we're open. because we, you know, just opening, we've been kind of taking it a little slow, and so we're hoping to add more days and longer hours and things like that as time goes on in the year. We're going to have some really awesome stuff going on around the Mineral Show, which is in February, which will be really fun. But yeah, so currently our hours are from 10 to 2, Monday through Friday. So we're hoping to add more days longer that we're open.
Cool. So definitely check out their, you guys have a Facebook and all that?
Yeah.
And a website and everything?
Yes.
We'll have all that up on the screen towards the end of the episode. Well, let's go check out a few more things and then we'll close up the episode.
Yeah.
All right, let's go. Guys, this has been incredible. And I mean, just like, these displays are absolutely mind-blowing that you guys have created in here. And I cannot thank you guys enough for sharing all of this museum with us and with our audience as well. Thank you guys so much.
Thank you,
We really
Chase.
appreciate it. Is there anything else that you guys would like to add to our audience out there? How can they get if they want to get a hold of you guys? How can they get a hold of you? If they want to come see the museum, how can they do that?
Sure. So, you know, we have a website. You can just Google the U of A Alfie Norville Gem and Mineral Museum. We are open to the public as of this week. If you're in the area, we would certainly welcome you to come in. We do guided tours periodically where we take people through and explain everything that we've done, much like we did for you earlier. We also have general admission. So if you find yourself anywhere near southern Arizona, please come and give us a visit.
For sure. Do you guys have any social media or anything like
We
that?
do. We're on Facebook, Instagram. We'll share all those links and you can share them with your viewers as well.
We'll put those up. Guys, this is definitely a place to stop if you're on vacation or if you live in the area. For sure, this is an incredible piece to put on your bucket list. Guys, thank you so much
Thank you,
for
Chase.
coming in. For
Appreciate it.
Thank you. Remember, guys, history rocks.